5 kilograms. And the rope is 100 meters, excuse me, long. And I've got them on the ground, and I want to pull them up to the window, 100 meters off the ground. And the rope happens to be, I don't know, how about a half a kilogram per linear foot? Question: how much work is required to get Archimedes up there? Would you guys agree that when it comes to Archimedes, unlike my slivers of water here, the amount of work is no calculus? You know, I think when it comes to taking the sliver down here or up here, pulling it up, it's going to require some calculus because I think, well, the distance changes depending on where the sliver is. I even think the volume changes. But I think when it comes to Archimedes, everything's a piece of cake. I'm going to separate this into 2 problems. Number 1, let's talk about the work involved in just taking Archimedes straight up 100 feet. I think the work involved with carrying him up, or pulling him up, is going to be nothing more than, well, his mass.
5 kilograms times gravity.
So 5 kilograms times gravity, which is 9.8. Times how much distance I have to push him up, or pull him up, I should say, which is going to be 100 meters. You know what? That's a really good point. So I was avoiding that issue. I think you're talking about the complex part of the problem. I was just imagining that this is magic. I'm pulling Archimedes straight up, there's no rope. But he's got a point. I think when it comes to the rope, I think the issue is more complex. Think about it. When I first start pulling the rope, I think there's quite a bit of force there, I have to exert. But once the rope's almost all the way up, I think there's very little, relatively little force. And so I think the force changes depending on where how much rope I've already gotten up there. So watch me in my usual lazy fashion. X-axis, Y-axis. Let's talk about a thin sliver of rope that's got a vertical dimension of delta Y. Let's talk about how much work is required in getting that ice sliver all the way up. First things first, let's talk about the amount of force needed to exert on that ice sliver to get it up. And I think the force needed to get it up is going to be computed in half. I think it's a 1/2 kilogram per. You guys look at my units. I really made a mistake. I don't want that, do I? Wasn't I measuring everything in international units? I'm so sorry. That's my mistake. Can I just very quickly change it to meters? Would you mind? My apologies. I'll be more careful. But you guys, look at the sliver of rope. How much length of rope do I have here? Delta Y units. And it's measured in meters. And if I multiply it by 1/2 kilograms per meter, I'm going to get the mass of that particular piece of rope, which is nothing more than 1/2 kilogram. So I think the force needed to exert on it is going to be 1/2 delta Y. Is that it?
What does 1/2 kilometer equal? The weight of the rope?
Yeah, but it's sort of like more of a unit weight. I'm saying for its big, long length of rope, every meter of it, every linear meter, is going to have a mass of 1/2 kilogram. So if I've got a thin sliver that's delta Y meters long in the rope, I think 1/2 kilograms per meter times that many meters is going to give me 1/2 kilograms. Kilograms measures what? What's that? Yeah, that's my whole point. Do I need something else here?
Yes.
So I need to introduce acceleration, which is
Gravity.
9.8, isn't it? So I think my force could be my mass times my acceleration. You're right. Multiplied by half is 4.9. You're right. I'm just being really lazy for you numbers, just so you can see where they're coming from. Oh no, I made a mistake. Well, I didn't make a mistake. I'm just not there yet. Actually, I want the work required in getting an ice sliver all the way to the top, but I think that's just going to be the force needed to serve an ice sliver times how far it needs to travel in the upwards direction. And I think that's merely going to be what I already have for my force. Times the distance, which is, I don't know, let's be lazy. Let's choose an arbitrary point in an ice sliver. Call it x sub I comma y sub I. I'm being silly, guys. X sub I is constantly 0. But I'm just trying to use my usual technique. I think the distance I need to go is a top height of 100 meters minus the low height of whatever this vertical position is, which I labeled as y sub I. So I think d sub I ends up being nothing more than 100 minus y sub I. Oh, you guys, check this out. This makes my life easy. I'm going to eventually integrate respect to y. I kind of like that. And therefore, the total work required in getting the entire rope up is going to be computed by looking at the limit of the Riemann sum of the w sub i's as n increases up bound. But that's merely going to give me the integral of my 4.9. Is that a 100 minus y with respect to y? Oh, by the way, these vertical green slivers stack up from what low extreme value in the y-axis to what upper extreme value in the y-axis. Sorry, you're right. I put a 1 there.
Isn't it the height of Archimedes to 100?
What a good point. Neglecting how the rope was attached, can we just pretend he really balances well? And the rope goes right to the middle of the platform. Aw, jeepers, you guys, I still haven't answered the question. I guess the work involved, the total work involved, is really going to be the sum of these work values. That'll be my 5 times my 9.8 times my 100 plus whatever the value of the integral is. Do you guys mind, just because I want to beat that clock, do you mind if I stop? I mean, the evaluation here is a piece of cake, isn't it? I'd just rather spend my time in class today looking at setting up a situation. Anything else?
What, in this example, what's the last one? The 5 times 9.8?
You know, this was nothing more than the amount of work required to take Archimedes down on the ground, and without any rope, just imagining how much work would be required getting straight up, moving 100 feet.
Oh, and
I said feet again, I meant 100 meters.
this is just the rope.
And that second integral just amounts to only how much work is required to get the rope all the way up, without Archimedes attached. And I just think the sum of those two values is the total work involved in the problem situation. Happy? 20 minutes. Do you think that's enough to give you 2 more examples? I'll stop. Just 2. It's a spring. And it's at rest when it's 20 meters long. It's a really big spring. And I want to find out how much work is required in stretching it from a length of 24 to 26 meters. Given that I already know a force of 5 newtons is required to stretch it. To a length of 22 meters. So, given this, determine the amount of work required to stretch it. What was the numbers I just made up? Was it 24 meters and 26 meters? So from 24 meters to 26 meters. Well, I don't know if you guys are familiar with this, but in standard basic introductory physics, by Hooke's law, I think the force needed to stretch a spring to a certain position is indeed going to be proportional to what that distance really is. And so in this particular example, I do think I can come up with the force function. Because I think with all the given garbage, the force exerted on a spring is going to be 5 newtons. In order to stretch at a total of, I forgot my number, was it 22? I can't remember. 22? 22?
22, yeah.
I can't hear you.
2 meters.
I think it's just 2. So how far I need to stretch it, so its length is 22 meters. That being the case, I think that constant in Hooke's law is merely going to be a 5/2. So, I think it's the case that the force function is going to be nothing more than 5/2 x. Let's drop it like a rock. Because I have a question yet. My question is, how much work is required to stretch this string from 24 to 26 meters? And I think when it comes to work, here too is simply going to be the product of the force and the distance. And I think it's going to be the product of the force and the distance. I think I should express this as an integral of my force function with respect to x.
Is it, right over there you had, it takes 5 units to stretch it to a length of 22 meters.
Yes.
Why is it 2 meters?
Because I think by Hooke's law, the force is proportional to how far I've stretched it. And since its natural length was already 20 meters, when I keep the spring at rest, then I think to stretch it to 22 meters, I stretch a total of 2 meters.
Yes, sorry. It's doing 24 and 26.
Thank you. That's what's next. So you're going to say, over here, I'm going to stretch it from 24 to 26 meters. And I'm going to evaluate this integral. I've lost it. What's my f of x? Oh, it's right there. But that's merely going to be a 5/4 x squared evaluated from here to here. Or shall I say 5/4 times, you guys always make me do all the work. Is that 20? Or shall I say 25? I lost my units. I said I lost my units. I'll
Joules.
say 3 times. Joules, because I've got newtons, meters. What's your joules? Kind of quick and easy application of work.
Why did you go from 4 to 6? Wasn't it 24?
Here's why, because I think that spring in its natural position is already 20 meters long. So to stretch it from 24 to 26 is stretching an additional distance of 4 to 6 meters.
Okay.
That's why I chose those 2 values. Come on, you guys piece of cake. Does that mean in 15 minutes I can finish our discussion with just one last example? Then you can leave, I won't talk anymore. You guys, I need some assumptions here. I'm deep underwater. And if I'm a point, not a human being, but just a point, right there, in which direction is the water coming in to give me a greater force? See, I don't think there is a direction to give me the greatest force. I think the force exerted on me due to the pressure of the water, due to I need the word hydrostatic pressure. It's the same. Here's another assumption you make. Well, maybe not an assumption. But you consider a piece of material that's horizontal in the water, parallel to the top of the water. I know I don't draw very well because I'm drawing in a 2-dimensional ink board, but I'm talking about 3-dimensional space. So I really meant that sliver of metal or whatever it is to be horizontal or parallel to the water level. What do you guys think is the force exerted on this object from the water above? What is that force?
Pressure times area.
Actually, yes. I want to justify that. So if you don't mind, can I take more baby steps? I think you can think of the force as just mass times acceleration. But the mass is nothing more than density times volume times acceleration. But you guys remember, I assume that plate underneath the water was parallel to the top surface. So I think wherever you are on the plate, the depth you're at is constant. And so I think I can think of the volume as the area of that plate times how deep it is times g. Or I can think of this as rho times g times depth times a. You guys, can can I just make up a whole man-made word out of thin air again, just like I did with work?